gentle and sketchy introduction to a very important recent area of combinatorics, or an area that really but was only introduced in the 90s, but has become a really central area, particularly over the last 5 years. So here's a very basic question. So Roth's theorem says that for every delta, if n is sufficiently large, then an A is a subset of 1 up to n with delta n elements, then it must contain a 3-term arithmetic progression. Okay, so we can make a definition for each delta. We can say that a set X is delta Roth if every subset of it with density at least delta contains a 3AP. So Roth's theorem says that if X is an interval, a sufficiently large interval, then it's delta Roth. So it's a very fundamental question: which sets are delta Roth? Well, this is probably too difficult. So as always, if something is too difficult, maybe they should instead try the random version of the question. Okay. So if, that's question 1, question 2, if X is a p-random subset of 1 up to n, so I mean take each element of 1 up to n independently with probability p, for which p is X likely to be delta Roth. Let's say with high probability. So in this form, what does Roth's theorem say? It says that if p is 1 and n is large, then X is delta Roth. So Roth for all delta, p equals 1 and large implies X delta Roth. Yep. Is it okay? Right. So we're looking at take fixed delta, take n very large, and take some p which can depend on n, take a random subset of 1 up to n by choosing each element independently with probability p, and ask if X is likely to be delta Roth, meaning if you take a delta proportion of the elements, then you have to find a 3AP. Okay? So, any guesses for which P work? So, Roth's theorem says P equals 1 works. Okay, great. What if P is very small? If P is really, really, really small, so P is a function of n, right? So if is really, really small, then well, X won't contain any 3-term arithmetic progressions at all. Right? So it definitely won't be delta Roth. Well, so how many 3APs do we expect? Well, each one is there with probability p cubed, and there are n squared of them, more or less. Right? Pick 2 of them, that determines the third. Well, 3 possibilities. Suppose that's much smaller than 1. So if p is much smaller than n to the minus 2 over 3. then you're not likely to get any at all. Right? Even in X. So in A, certainly not. Okay, but that seems a bit strong, right? So we're allowed to remove almost all of X to destroy them. So we should be able to do better. What if this number, instead of being much smaller than 1, was a bit bigger? What if it was about the size of X? Or just a bit smaller than the size of X? Then what could you do? You pick your random subset X. It's so sparse that the number of 3-term arithmetic progressions is much smaller than the number of elements. You just destroy them one by one. Right? You just pick a 3-term arithmetic progression, pick an element, throw it out. And continue until you've destroyed them all. And then you'll have a set A that's just a subset of X, which will actually be more than half of X, with no 3-term AP. Now how big is X? It's about P times N. So if P squared times N is much smaller than 1, then we have this. So if P is much smaller than not n to the minus 2/3, just n to the minus 1/2, you're still, with high probability, not delta Roth. Because you're likely to have fewer than Pn 3-term APs, and you can easily destroy them all just by removing one vertex from each. It's a lovely theorem of Koyakawa from Sao Paulo, Wuchak and Erdös from I think 96, where they show that this is really the best you can do. They show that if, so for every delta there exists a C, so that if P is bigger than C over root n, then X is delta Roth with high probability. So it should be, well, perhaps somewhat surprising. So note that it's not even obvious that this, the probability of being delta Roth is increasing in P. Right? So it feels like perhaps it should be, but as X increases, then, as P increases, then your set X is getting bigger. And so you have, your set A has to get bigger, but you also have more choice about what things to throw away. Anyway, at least in this case, it seems there really is a threshold. This threshold is 1 over root n. As soon as you have a large constant times root n elements, and they're random, then just any positive fraction of them will give you a three-term AP. Okay. Let me give you another similar problem. Perhaps this one was easier to think about. I'm not sure. So Mantel says that if G is a subgraph of the complete graph with at least a half plus delta n choose 2 edges, then there exists a triangle in G. Okay, so I'm giving a very weak version with a delta in. So in fact, anything bigger than n squared over 4 plus 1 works. But maybe you'll see why in a second. Say H is delta Mantel if every subgraph of H with at least a half plus delta proportion of the edges contains a triangle. So Mantel's theorem says that the complete graph is delta Mantel. The question is, for which P is GNP delta Mantel. Well, once again, if P is so small that there aren't very many triangles, then it should be pretty easy to destroy them. So what? So what is the expected number of triangles? P cubed times n cubed this time. And suppose this is much smaller than Pn squared, which is the number of edges in GMP. So if P cubed n cubed is much smaller than the number of edges of GMP, which is basically Pn squared, then we can easily destroy all triangles. Right. Just look at every triangle, pick an edge of it, and throw it away. You only have to do that about P cubed n cubed times. You have Pn squared edges, so you can easily do it, and you still have almost all your edges. So this is if P squared n is much smaller than 1. So if P is much smaller than 1 over root n, again, then GMP is not delta Mantel. Well, it's not even a quarter Mantel, let alone delta Mantel. Is it okay? So theorem. Now I have to remember who actually proved this. I think Babai, Simonovitz and Spencer. Maybe. I don't promise. That for all delta there exists a C such that if P is bigger than C over root n, then GMP is delta Mantel with high probability. And generally you can ask the following question. That's the definition. The extremal number of GH is going to be equal to the maximum number of edges of a graph F, such that F is a subgraph of G and F is H-free. So what's the extremal number NH? It's just the extremal number of KNH. Right? And the question is, what is the extremal number of GMP H? In particular, for which P is the extremal number. Let me write it up here. Sorry, a bit bigger. Extremal number of GMP H should be equal to what? 1 minus 1 over chi of H minus 1 plus little o1 times the number of edges of GMP for which P? So this theorem determines the threshold for this property for triangles. And we can ask the same thing for Ramsey problems. Where shall I put this? It's more over here. So Ramsey says that if you have a colouring from the edges of Kn to, let's say, 0, 1, there exists a monochromatic KK. Right? This is what the two-colour finite Ramsey theorem says. So we can do the same thing on any graph G. Say that a graph G is, I don't know, I guess K Ramsey or KK Ramsey if whenever you colour the edges of G with two colours, then there exists a monochromatic copy of KK. The question for which P is GMP KK Ramsey. And a lot of these problems were solved by Rudler and Jinsky in the 90s. Okay. So we have a whole family of problems which kind of look similar. Right? They're the same. The theme is the same. That you have some theorem that you know on the complete graph or on the set 1 up to n, and you'd like to ask if So you can say do the same with Schur's theorem, right? You look for a solution x plus y equals z if you multicolor subsets of 1 up to n. So you have a theorem that you can prove in the dense case, and you'd like to ask whether it still holds in the sparse case, and how sparse you can make it. And one of the big problems in proving these kind of things is that the regularity lemma doesn't hold in the sparse case. So there are things that you can prove in the dense case, well, so I lie a little, you can prove a version of the regularity lemma in the sparse case very easily, but you can't use the embedding lemma. The embedding lemma doesn't work. Okay? So the regularity lemma is not useless, but much less useful than you might hope. So actually, KLR, Koyakawa, Wuchek, and Rödel came up with a conjecture about epsilon regular pairs in the sparse case, which would help with this problem. This has recently been solved, and so hopefully the situation will change. But anyway, so this is a basic problem that sparse things are very difficult to deal with. And that's part of the problem, that this problem was open until, well, the paper hasn't even appeared yet, till it was solved recently by a guy called Matthias Schacht, and also by David Conlon and Tim Gowers. So David gave a mini course, which I think at least some of you came to. So let me tell you, basically they solved all of these problems. Well, between them at least. And they did so by putting all of these problems into a common language. So let me give you a very rough outline of what they proved. So all of these problems fit into the same setting. And the setting is basically that of k-uniform hypergraphs. So what is the hypergraph in each case? So for Roth, k equals 3, and the hypergraph encodes 3 APs in 1 up to n. So the vertex set is 1 up to n, and the edges are the triples which form 3-term APs. So similarly for Szemerédi's theorem, k is general, and h encodes k-term APs. For, say, Mantel's theorem, then we want to encode triangles. So you might think that the thing to do is let the vertex set be 1 up to n and encode triples which form triangles of vertices. That's the wrong thing to do. The vertex set of our hypergraph is going to be the edge set of the complete graph. And the edges, so I should say k equals 3 and h encodes triangles. Okay? So the edges, the hyperedges of this hypergraph are triples of edges which form triangles. This might seem silly until you think about the case in general. So if you're doing Erdös-Stone, then suddenly you can take the same vertex set, k equals the number of edges of our graph H, H encodes copies of H in Kn. So if your vertex set of your hypergraph is the edge set of the complete graph, then it's very easy to encode copies of a particular subgraph because you're just looking at the edges. Right? So it's a K-uniform hypergraph where K is the number of edges of our small graph H. Does that make sense? Okay. So what does Schacht prove? So yeah, Schacht and Conlon-Gauss prove slightly different things, I should say. So Schacht said something like the following. So if H is K-uniform and satisfies the following two things, and is alpha dense. So what do I mean by alpha dense? By alpha dense I mean there exists a theorem in the dense case. Okay? So in each case we started with the dense theorem. The Erdös-Stone theorem meant the theorem held for the complete graph. Ramsey's theorem says the theorem holds for the complete graph. Szemerédi's theorem says the theorem holds for the set 1 up to n. So what's alpha? Alpha is the threshold at which it works. So in Szemerédi's theorem, alpha is 0. In Erdös-Stone theorem, alpha is 1 minus 1 over chi of h minus 1. And it says something a little more than that. It says if A is a subset of the number of vertices of H, and the size of alpha of A is at least alpha plus delta times the number of vertices of H, then the number of edges of H contained in A is at least epsilon proportion of all of them. So what does this say? For the Erdös-Stone theorem, it says if you start with 1 minus 1 over chi of h minus 1 plus delta times n choose 2 edges, you contain not just one copy of H, but you contain as many as you could hope for. You contain a positive proportion of all of them. And we prove that because that's what the Szemerédi's regularity lemma proof gives. Remember, in the embedding lemma, we didn't just find one triangle, we found n cubed triangles. Okay, delta cubed times n cubed. Right? We found a positive proportion of all triangles when we have a triple that's epsilon regular and delta dense. Right? So this is crucial in this case. So the input for this theorem is that you need to have a dense theorem of this form, where if you have a little more than the extremal number, say delta more, then you have a positive proportion of all solutions. Okay. And what else did he assume? He assumed something called KP bounded, which I don't really want to get into. It just means that P is sufficiently large so that the trivial... So in each case, the trivial result was if P is really small, there are so few copies of our object that we can destroy them all really easily. And it's basically a way of encoding that you're bigger than that threshold. Okay? So too big, or P too big, for the theorem to fail trivially. So the actual condition is slightly technical, but that's basically what it says. So actually it says something sort of about the hypergraph as well, but it's not so straightforward to understand. But anyway, so what this gives you the correct threshold for Szemerédi's theorem and the correct threshold for Erdös-Stone for any graph H. So it really is a very sensible condition. It's a very natural one. This implies if X is a subset of the vertices of H is P random, well, again I cheat slightly, really Q random where Q is a large constant times bigger, but let's not worry, let's change the definition. It's P random, then, oops, and A is a subset of X of size at least alpha plus delta times X, then there exists an edge of H in A. Okay. So what Stone basically tells you is that if you have a theorem in the dense case of this particular form, so a strong theorem in the dense case, and your P is big enough so the theorem isn't trivially false, then any P random subset, for any P random subset, you take a subset of size alpha plus delta, so the same threshold you got in the dense case, then you must be able to find an edge of the hypergraph, i.e. one of your forbidden objects. So you must be able to find a KAP, or a copy of H. Okay. So the proof of this is very beautiful and not all that hard to follow, actually. So I've taught it already twice before, and it was okay. So I'm afraid if we had one more class, then I would probably tell you the proof. But it's worth looking up. So this solves basically all of these questions. And, well, so I told you all of the extremal questions. There's also a lot of stability questions. How about Erdös-Stone stability that I just told you about? So it says that if you're triangle free and have almost half the edges, then you're close to being bipartite. Something like, if triangle free, at least a half minus alpha, and choose two edges, then close to bipartite. So he does the same thing in the random graph again. Suppose you have a random graph, GMP, and you take a subgraph of it that's triangle free and has almost half of the edges of GMP. Must it be close to bipartite? And for which P? This says it's true when P equals 1. And this was proved by Conlon and Gowers. So this also hasn't appeared yet. Together with not all of the things that Schack can prove, but many of them. So they did it in a very general setting again. So basically the same setting. But they used a totally different method. So Schack looks at this random set X. He basically splits it up into lots of small parts. and then looks at them one by one. And they're not all the same size, they're growing, but let's not worry about that. And he says, all right, let's start looking for the first edge of H. And then let's look for the second edge of H, and then the third one. And he does this for each edge. He has a large number of random sets, and he basically builds up more and more forbidden structures until by the end you have so many things you could hit, you have to hit one. It's a bit like in the proof of van der Waerden, if you remember from way, way back at the start, that we build up things, we look for these, S color-focused arithmetic progressions. We just have so many things that could be the next thing you want that you have to hit one of them. You're forced to. So it's more complicated here, but it's basically the same idea. So Conlon-Gauss is something completely different. They look at functions. So those of you in David's course maybe saw a bit of this. They tend to look at everything as a system of functions, and they look at the expected number of things, and they apply the Hahn-Banach theorem, and it's all some very complicated analysis. And they get a result that's weaker in some ways, but stronger in others. So, I don't know. So I perhaps can't explain this very well, because I don't really understand it that well, I must admit. It's very complicated and very beautiful. But anyway, so they can prove these stability theorems. It turns out that, in fact, Schach's method can also be used to prove stability theorems. This was only noticed a few months ago by Wojtek, who was giving the other mini course, who found a clever way of adapting Schach's method. So, in fact, Schach's method seems to give basically everything. Well, not quite everything. So, my final bit of advertising in the last 10 minutes. I want to tell a theorem of Balog and myself and Samoti. This is Wojtek, who gave the mini course. This is basically what he was talking about for those who were there, but, well, he only really got onto it near the end. This says something like the following. So if H is K uniform and you have some P and they have some certain properties which are very simple, but they're basically to do with the maximum degrees of H, or most something or other. So by this I mean, let's think about graphs again. I mean, suppose you take a subgraph of H with L edges. How many ways can you extend it to find a copy of H? That's the maximum degree. So the maximum overall subgraph of size L. Then what? Then basically you can count independent sets in these graphs. They do something slightly different. So I don't know quite the right way to say this. So the actual result is somewhat technical. Basically, you have some functions into small sets and some other function from the small sets to the complement of some family. Okay, this is the family of independent sets. So this is going to make no sense at all. But let me try and explain what it really means, or what you can do with it. So basically, F is a family of things which are alpha dense. So it's like the the collection of sets of size at least delta n in n has lots of 3 APs in it. The set of graphs which have at least a half plus delta proportion of edges contain lots of triangles, something like that. Or in this case, the set of things which have at least this many edges and are far from being bipartite. So it basically allows you to encode independent sets as a small set. So there aren't very many of these. And you encode the small sets as things which are not in these families. So that will sound like total gibberish. But the proof of this is reasonably simple. It's basically what Wojtek talked about, for those who were there. And what does it give you? It gives you all of these things. It gives you everything, so not quite everything that Schacht could prove. So instead of doing Erdös-Stone for every graph H, we only do it for balanced H, but okay. It gives you all the stability results of Konron-Gowers. It gives you the KLR conjecture. And it gives you the following thing. So just to link back to what I did in the first half, so it allows you to prove the Erdős-Fraenkel-Rödel theorem for sets of size m. So this implies many things. Szemerédi, Erdös-Stone, etc. It implies Erdős-Fraenkel-Rödel without using the regularity lemma. And it also implies, so in the following slightly more precise or more refined version, says that the number of H-free graphs on n vertices and with m edges is basically the extremal number of H, choose m, times some small constant. So I need m bigger than c, well, we should say the threshold, which turns out to be n to the 2 minus 1 over m of h. So this m of h, if you ever did the exercise in the random graph section, which asked you what's the threshold for, well, it's not quite true. So basically this is the threshold for the appearance not of one copy of H, but of many copies. Many copies being that you can't destroy them easily. So it's the same threshold as here. Okay. So if you have fewer than this number of edges, you have so few copies of H, you can destroy them all easily. So it's the correct thing. Right? So this implies the theorem that we proved the first hour. Right? Because if you just sum over m, then you'll get 2 to the extremal number with a 2 to the delta n squared. Okay. So this can be seen as a sparse version of sparse Erdős-Fraenkel-Rödel. Anyway, so I apologize if that made no sense at all. It was supposed to be a sort of propaganda for the kind of things that people here at IMPA do, the kind of things that if you want to come to IMPA, then you can work on. So, anyway, so this is the end of the course. Apologies for not sending the exam round yet. I will send the exam tonight. So if you don't receive an exam by midnight tonight, then send me an email telling me that I got your email address wrong or something. Okay? And I guess the deadline is a week after I send it, so the end of Monday next week. Yeah. And if you send me plaintive emails saying you need an extra day or two, then that's okay. I'm not going to be too strict. Yeah. Cool. And thank you all for sticking through to the end. Cool. We're done.